Picture this. It's 2 a.m., your phone is blowing up with PagerDuty alerts, and your production database is corrupting records silently. The culprit? Code that passed every AI-generated test, reviewed by the same AI that wrote it. No red flags, no warnings, just confident, broken output shipped straight to your users. This is not a hypothetical. Developers across the industry are falling into the exact same trap. They hand a single AI model a task, the model reviews its own work, declares it correct, and they ship it. But here's the brutal truth. A model cannot see its own blind spots. It will hallucinate a missing edge case, a function that doesn't exist, or misunderstand your database schema, and then confidently tell you everything looks great. The false confidence is the real danger, not the error itself. By the end of this lecture, you will have a concrete system to make that scenario structurally impossible. And it starts with understanding why one model is never enough. So what is the structural fix? This is where Claude Octopus enters the picture. Instead of trusting one model's verdict, Octopus route your code, test generation, architecture decision through up to 8 independent AI models simultaneously. Each model produces its own answer without seeing the others. Then comes the consensus gate. If fewer than 74% of the models agree on the output, the result does not pass. It gets flagged, debated, and refined. Think of it like a senior engineering review committee where every member has a veto. The disagreement between models is not a problem to suppress, it is the most valuable signal in the entire pipeline. When GPT-4 says the function is correct and Claude 3.55 flags a race condition and Gemini questions the schema assumption, that disagreement just saved your production system. The 74% threshold is not arbitrary, it is calibrated so that genuine edge cases surface before they reach users. But wait, what exactly does this system look like under the hood? That is precisely what the next section will show you. Let's be specific about what you are going to walk away with after this lecture, not vague awareness, but executable skills. First, you will know how to install Claude Octopus through all 4 supported methods: pip package, Docker container, GitHub code spaces, and direct API integration, so you can use it in any environment you already work in. Second, you will be able to configure and run a multi-model debate session where you define the models, set the consensus threshold, and interpret the disagreement report. Third, you will know how to wire consensus gates into your existing CI/CD pipeline so that AI-generated code never merges without passing the threshold. And fourth, and this is the one most people skip, you will know how to write custom plugin hooks that extend Octopus with your own domain-specific validators. Each of these skills builds on the last. Skip one and the pipeline breaks. But follow the sequence in this lecture, and by the end you will have a working orchestration layer running against your own repository. Now, here is the part that changes how you think about AI development entirely. And I am going to show you something most developers do not believe is possible yet. Here is the concept that will make you rethink what AI-assisted development can actually look like. Inside Claude Octopus, there is a pipeline configuration called the dark factory. The name comes from manufacturing, a fully automated factory that runs in the dark because no humans need to be present. In software terms, you feed in a specification document, a plain English description of what the software should do, and the dark factory pipeline handles everything else. It runs the multi-model debate to understand the spec. It generates implementation candidates. It's them against a consensus-verified test suite. It refactors until the threshold is met. And it outputs working, tested, deployable software, with zero manual intervention in between. Now, I want to be precise. This is not magic, and it is not always appropriate. There are decisions that require human judgment and domain context that no pipeline should bypass. But for well-scoped, well-specified tasks, Dark Factory is a working reality right now, built on top of the orchestration principles we cover in this lecture. In the next chapter, we go inside the architecture, the exact components that make this possible, and the design decisions you need to understand before you build anything on top of it. Let's be precise about what Claude Octopus actually is, because the word orchestrator gets thrown around loosely. Claude Octopus is a plugin architecture that sits above your AI models and coordinates up to 8 of them simultaneously. We're talking Claude, Codex, Gemini, Codex, Oyama Perplexity, and OpenRouter, each one a specific role. Think of it like a conductor in front of 8 musicians. The conductor doesn't play an instrument, controls timing, balance, and harmony. Claude Octopus doesn't generate code itself. It routes, delegates, collects, and reconciles. That distinction is critical. Most developers miss it and end up treating Octopus like a better chatbot. And that's exactly the trap we're going to dismantle. Stay with me, because the model map you're about to see changes how you think about every AI tool you currently use. Here is the core insight that justifies the entire architecture. Every AI model has blind spots, not random errors, but systematic, predictable gaps baked into its training data and optimization objective. Claude tends to over-explain. Codex under-documents edge cases. Gemini occasionally drifts on long context. No single model self-corrects its own blind spots. It literally cannot see what it cannot see. Cross-validation between models is how you surface those errors. When you run the same output through 4 models, and one of them flags a logic flaw the others missed, you have just caught a production bug that would have shipped. That is ensemble AI applied to software development, the same principle that makes random forests more accurate than any single decision tree. But here is the uncomfortable question you should be asking right now. If cross-validation is so powerful, why isn't every team already doing it? The answer in the next scene. The reason most teams aren't doing cross-validation is that their existing tools weren't built for it. Take Superpowers, a popular AI coding assistant. It is a single-agent refinement loop. You prompt it, it responds. You refine, it improves. That workflow is excellent for isolated, well-scoped tasks, a function, a regex, a unit test. Octopus is something different in kind, not just degree. It is a multi-agent mutual verification system. Multiple models independently assess the same output and vote on its validity. Superpowers is a skilled, solo developer iterating on a problem. Octopus is a senior engineering review panel where every reviewer has different expertise and none of them can collude. Knowing which tool to reach for is half the battle. Use Superpowers for speed on small tasks. Use Octopus when the cost of a wrong answer is high. In the next section, we'll see exactly how Octopus structures that verification process into 4 stages. And the first stage will surprise you. Octopus doesn't just throw your prompt at 8 models and hope for the best. Every task processed by the orchestrator follows a 4-stage methodology called D4. Discover, define, develop, deliver. Stage 1, discover. The system interrogates the task, identifies ambiguities, and pulls in relevant context from connected sources. Stage 2, define. It structures the problem into a spec that all models can operate on consistently. Stage 3, develop. This is where the models do actual work, generating, analyzing, or transforming content in parallel. Stage 4, deliver. Outputs are reconciled, the consensus gate is applied, and a validated result is returned. What makes D4 powerful is that it transforms a vague prompt into a structured contract before any model touches it. Ad hoc prompting skips stages 1 and 2 entirely, and that is where most AI-generated bugs are born. The next scene will show you exactly what happens when a real task travels through all 4 of these stages. Let's make this concrete. Say your task is, build an authentication middleware for an Express API. Watch what D4 does with that. At T0, discover, Octopus identifies missing requirements. Which auth strategy, JDWT or session? What token expiration? Are there refresh tokens? At T15 seconds, define outputs a structured spec, token type confirmed as JDWT, expiry set to 900 seconds, refresh flow included. At T40, develop runs 4 models in parallel. One generates the middleware, one reviews for security holes, one checks against OWASP top 10, one writes the test suite. At T90, deliver reconciles the 4 outputs, flags a disagreement on error handling between 2 models, routes that specific section back for revision, and at T120, a consensus-validated middleware is returned. Compare that to a raw prompt to a single model, you get code in 10 seconds with 0 of those checkpoints. Fast, yes. But would you deploy it without review? That's the trade-off you've been making, and the methodology is the answer. The deeper value of D4 isn't just quality, it's consistency and repeatability at team scale. When every developer on your team uses the same 4-stage pipeline, AI outputs become auditable. You can trace exactly which stage introduced an ambiguity, which model flagged a disagreement, and which decision was made at the defined checkpoint. That is something you cannot do with ad hoc prompting. You get outputs with no lineage, no audit trail, and no way to reproduce the reasoning. In enterprise environments, that lack of traceability is a compliance and governance risk. D4 solves it structurally. Think of it as a manufacturing quality system for AI outputs. The same principle Toyota applied to car assembly with standardized work instructions. The methodology is what separates a toy project from production-grade AI-assisted development. And now that you understand the piping, you need to understand the gate that sits at the end of it, the consensus mechanism that either approves or blocks the output. That gate has a specific threshold, and the reasoning behind it is more rigorous than you might expect. At the end of every developed stage, Octopus runs every participating model's output through consensus gate. The threshold is 75%. Here is exactly how it works. Each model casts a vote, approve or reject, based on its independent assessment of the output against the spec defined in stage 2. If 6 out of 8 models vote approve, that is 75%, the output passes. If 5 vote approve, that is 62.1%, the output is blocked. Why 2% specifically? Because at that threshold, you need at least 3 models to disagree before an output fails. A single outlier model with a quirky training bias cannot veto an otherwise sound output. But a genuine fault that 3 or more models independently identify is almost certainly real. This is not arbitrary, it mirrors the quorum rules used in distributed systems consensus protocols like Raft and Paxos, where a majority plus 1 prevents split-brain scenarios. The threshold is a deliberate engineering decision, not a tunable knob someone set to a round number. But what actually happens when an output fails that gate? The answer is more interesting than a simple rejection. When an output fails the 74% consensus gate, it does not simply disappear. The failure is structured and actionable. Step 1. The output is rejected and flagged with a disagreement report. This includes which models voted reject and what reasoning each one logged. Step 2. The system identifies the specific sections of the output where disagreement is concentrated. It does not rerun the entire task. It surgically routes only the contested sections back to the develop stage for targeted revision. Step 3. The revised sections are re-evaluated and a new vote is cast. If consensus is reached, the corrected output proceeds to deliver. If it fails again, a human escalation flag is raised, because at that point, the disagreement likely reflects a genuine ambiguity in the original spec that no model can resolve algorithmically. This is a safety mechanism with teeth. It is not a soft warning, it is a hard production blocker. Nothing ships without passing the gate. That brings up a comparison that will reframe how you think about your current code review process entirely. Let's put the consensus gate next to the thing it most closely resembles: human code review. In a traditional pull request review, 1 or 2 engineers read through changes, leave comments, and approve or block the merge. The consensus gate does something structurally similar, but the differences are stark. Speed. Human review averages 4 to 24 hours depending on team load. The consensus gate runs in under 2 minutes. Coverage. Human reviewers catch logic errors and architecture concerns well. Consistently miss certain classes of security vulnerabilities and performance regressions, especially under time pressure. The consensus gate, because different models specialize in different failure modes, covers a broader surface area. However, and this matters, human reviewers understand business context, implicit requirements, and organizational conventions that no model currently captures. The consensus gate is not a replacement for human oversight. It is a first-pass filter that elevates the quality of what human reviewers actually see. Used together, they are stronger than either alone. That is the governance model Octopus is built for. In the next chapter, we go deeper into what the system actually does. Because 32 personas, 48 commands, and 51 skills is not a feature list, it is a design philosophy. And understanding that philosophy will change how you architect AI-assisted workflows from this point forward. Here is where Octopus starts pulling away from every other AI wrapper you have tried. It ships with 32 pre-built personas, not just labels, but deeply engineered role configurations. Think of a security auditor persona that already knows OWASP top 10, threat modeling frameworks, and secure coding patterns before you type a single word. Or a backend architect persona loaded with microservices trade-offs, CAP theorem reasoning, and database schema heuristics baked right in. The table on screen shows the 4 major persona categories: security, architecture, development, and DevOps. Each category holds between 6 and 10 specialists. The key insight is this persona is not a job title. It is a compressed domain knowledge package. And the question you should be asking right now is, what exactly separates a persona from just writing a good system prompt yourself? Selecting the right persona manually is always an option, but Octopus does not require it. The system reads your task description, extracts intent signals, and maps them to the most appropriate specialist automatically. The process works in 4 stages. First, you submit a task. Second, the intent parser identifies domain signals, keywords like authentication bypass, latency spike, or refactor to solid. Third, a scoring engine ranks persona fit based on those signals. Fourth, the matched persona activates and configures the AI context before your first token is even generated. This by the time you see a response, the AI is already operating as a seasoned security auditor, or a battle-tested SRE, not a blank generalist. The practical implication is enormous. You stop wasting the first 5 messages of every conversation just establishing who the AI should be. But here is the part that surprises most developers: the automatic selection is not always right. And knowing when to override it manually is a skill worth developing. Let's settle the most common objection. I can just write a good system prompt myself. You can. But compare what that actually looks like side by side. A raw system prompt gives you a single instruction block you write from scratch every session. You carry the cognitive load of knowing what a security auditor should know. You rewrite it differently each time. You miss edge cases. A pre-built persona, on the other hand, is a versioned, community-refined role configuration that encodes hundreds of hours of prompt engineering across real-world security, architecture, and development workflows. It does not drift between sessions. It is testable. It is composable with commands and skills. The gap is not cosmetic. It is the difference between a sticky note and a professional playbook. And this distinction matters even more when you see what happens when personas are combined with the 48/commands. Which is exactly where we are going next. 48/commands. That number sounds overwhelming until you realize you will use about 6 of them for 90% of your work. Let me walk you through the critical 6. First, Octo Embrace. This is your codebase onboarding command. You point it at a repository, and it builds a full mental model of the project structure, dependencies, and conventions. Second, Octo Factory spins up a full-feature scaffold, routes, controllers, tests, and documentation in one shot. Third, Octo Debate forces the AI to argue multiple architectural positions before committing to a recommendation. Fourth, Octo Research runs a structured deep dive on a technology question with source attribution. Fifth, Octo Security activates a full OWASP-aligned security audit pipeline against your code. Sixth, Octo DDD generates a test-first scaffold before any implementation code is written. Each command is more than a keyword. It is a pre-wired workflow with its own persona, skill chain, and output format. The surprising part comes next. There is one command that makes all the others optional. The one command that makes all the others optional is Octo Auto. This is the smart router. Instead of you deciding which workflow to invoke, you describe what you want in plain English and Octo Auto parses your intent, scores it against all 48 available workflows, and selects the best fit command pipeline automatically. So if you type Octo Auto, I need to add rate limiting to the API and make sure it is secure. The router detects both an implementation intent and a security intent, and it chains Octo Factory with Octo Security behind the scenes without you specifying either. This sounds almost too convenient, which is exactly why most developers distrust it at first. But the routing logic is transparent. Octopus shows you which workflow it selected and why before executing. You can override, modify, or reject the routing decision at any point. Think of Octo Auto as the senior engineer who reads your ticket and knows exactly which team to hand it to. Except it does not take a 2-day sprint planning meeting to get there. Now let's look at command chaining, because this is where the real productivity multiplier lives. Individual commands are powerful. Chained commands are a different category of tool. Here is a real example. You need to build a new API endpoint, audit it for security vulnerabilities, write tests, and generate OpenAPI documentation. Manually, that is 4 separate conversations with an AI, each requiring context reestablishment. With Octopus command chaining, you compose it as a pipeline. Octo Factory creates the scaffold, pipes its output directly into Octo Security for an immediate audit pass, then pipes the security-approved code into Octo HTTDA for test generation, and finally into Octo Docs for documentation output. The output of each command becomes the input context of the next. No reprompting. No context loss. No copy-paste between sessions. This is the architectural pattern that the previous chapter set up, and now you can see it executing in practice. Up next, we go one level deeper into the building blocks that make these commands composable in the first place. The 51 skill modules. If personas are the specialists and commands are the workflows, then skill modules are the atomic units, the actual intelligence building blocks that everything else is assembled from. Octopus ships with 51 of them. Think of each skill module as a focused, reusable micro capability. Things like analyze cyclomatic complexity, generate SQL migration script, identify race conditions, produce mermaquence diagram, or write RFC-style technical spec. These are not prompts. They are parameterized, testable modules with defined inputs, outputs, and quality criteria. The mind map on screen organizes them into 5 clusters: code quality, security analysis, architecture, testing, and documentation. The critical design insight is that any command or persona can invoke any combination of these modules. A security auditor persona in Octo Security might invoke 5 skill modules internally: threat source mapping, dependency vulnerability scan, input validation check, auth flow analysis, and findings report generation, all triggered by a single command. Here is the question worth sitting with. If skills are this modular, what happens when you stack them in unexpected combinations? Let's make this concrete with a worked example, because abstract modularity is easy to say and hard to visualize. Imagine the task: perform a security audit on a new authentication service, scaffold its test suite, and produce developer documentation. Without skill stacking, you run 3 separate workflows, manually transfer context between them, and hope for consistency. With skill stacking in Octopus, the process decomposes like this. Step 1. The security auditor persona activates and invokes the authflow auditor skill plus the threat surface mapper skill. Step 2. The audit findings feed directly into the edge case identifier skill, which surfaces untested failure paths. Step 3. The TDD scaffold generator skill consumes both the original code and the identified edge cases to produce test scaffolding. Step 4. The RFC template generator skill takes the audit summary and test structure and produces a complete technical specification document. 1 task. 4 skill modules. 0 context re-entry. The output quality is higher than any individual AI session because each skill module enforces its own quality criteria on the data it receives. What you are seeing here is the DRY principle applied not just to code, but to AI reasoning itself. Here is the principle that ties the entire feature stack together. Don't repeat yourself, applied not to your code, to your AI workflows. Every developer who works without skill modules ends up reprompting the same reasoning logic across every project, session, every team member. How should I structure this prompt for a security review? Let me write it again from scratch. That is prompt duplication, the AI equivalent of copy-pasting business logic instead of writing a function. Skill modules solve this at the infrastructure level. You define the reasoning pattern once. It executes consistently across every invocation. It is versioned. It is shared across your team. And when you discover a better approach, you update one module and every workflow that uses it improves immediately. The keywords on screen summarize the 3-layer stack we covered in this chapter. 32 personas for domain expertise, CalTweet commands for workflow control, 51 skills for atomic composability. In the next chapter, we move from theory to terminal. You will see how to install Octopus, run it for the first time, and configure your first persona command skill pipeline from a blank environment. If you have ever struggled with AI tool setup, that takes longer than the problem it solves. What comes next is worth your attention. Now that you know what Octopus can do, 32 personas, 48 commands, 51 skills, the next question is how do you actually get it running? There are 4 distinct installation paths. Picking the wrong one wastes hours. The Claude Code plugin is your best bet if you're already in Anthropic's ecosystem. It installs as a native extension with 0 friction. The Cursor MCP server route is ideal for teams already using Cursor as their primary IDE, since it plugs directly into the MCP protocol layer. Codex CLI is the terminal first option, no GUI, maximum scriptability, perfect for CI pipelines. And OpenCode is the fully open source self-hosted path, giving you complete control at the cost of more setup time. Each method has hard prerequisites. Don't skip this slide. Choosing wrong means reinstalling from scratch, and that decision tree is coming up next. For most developers watching this, the fastest path to a Octopus install is the Claude-only setup. No juggling multiple API keys, no provider configuration files, no local model downloads, just 3 steps. First, install the Claude Code plugin from the marketplace. VS Code and JetBrains are both supported. Second, paste your Anthropic API key into the plugin settings. Third, init command will disk Octopus config directory. That's it. You're operational in under 5 minutes. The reason I recommend this as a starting point, even for teams, is that it gives you a working baseline to validate your workflow before layering in additional providers. Get one provider working correctly first, then expand. But here's where most developers make their first mistake with multi-provider setups. And the decision tree in the next scene will save you from it. The question of which installation method to choose isn't just about preference, it maps directly to your team structure and environment. Here's the decision framework. Solo developer with an Anthropic key, Claude Code plugin, no debate, using Cursor as your team's standard IDE. MCP server is the only path that keeps everyone in sync. Need to run Octopus inside automated pipelines without a human in the loop. Codex CLI is designed for exactly that. And if your organization has data sovereignty requirements, meaning model outputs can't touch external AIs, OpenCode self-hosted is your only compliant option. The most common trap is teams defaulting to whatever looks simplest, then discovering 6 weeks in that it doesn't support their actual workflow. Match the method to your constraint, not your comfort level. Next, we'll tackle something that genuinely surprises people. 5 providers you can configure at 0 cost, and how they stack up against each other. Here's something the Octopus documentation buries in a footnote, but deserves a headline. You can run a fully multi-provider Octopus setup at 0 ongoing cost. 5 providers are available for free, each requiring a different activation path. Codex requires an OpenAI free-tier API key, rate limited but functional for development work. Gemini connects via Google AI Studio, which offers a generous free quota. GitHub Copilot If you already have a subscription through your organization or student plan, integrates directly with no additional key. Qwen, Alibaba's model, is accessible with the Dash-Scope API with a free tier that's surprisingly capable for code tasks. And Ollama runs entirely on your local machine, no API key, no external calls, no cost ever. The catch with each of these is configuration format. Octopus expects a specific provider block syntax, and one misplaced field silently disables the provider. Let me show you exactly what each one needs. Before you add every free provider to your config, you need to understand one fundamental trade-off: cloud versus local. Providers, Codex, Gemini, Pilot, Qwen, give you powerful models with no hardware, but every prompt leaves your machine. For most development work, that's fine, but for code bases with proprietary algorithms or sensitive business logic, that's a real risk. Ollama flips this entirely. Your code never leaves localhost, latency is measured in milliseconds, not seconds over the network, and it works completely offline. The downside is that local models are smaller. Ollama running Llama 3 or CodeGemma on consumer hardware is capable, but not equal to GPT-4 class cloud models. The practical recommendation: use cloud providers for architecture exploration and ideation, switch to Ollama for tasks touching sensitive code. Octopus lets you configure both simultaneously and route tasks by sensitivity level. That routing configuration is exactly what we'll cover when we hit advanced workflows in the next chapter. You've configured your providers, but how do you know they're actually working? Octopus ships with a built-in health check command that pings every configured provider and reports back connection status, model availability, and response latency. Run Octopus provider check all and you'll see a provider status table in your terminal within seconds. If a provider's red, the error message tells you exactly what's wrong: bad API key, wrong model name, endpoint unreachable. Don't skip this step before running your first real task. I've seen developers spend an hour debugging a failed Octopus run only to discover that one provider was misconfigured and silently falling back to a default they didn't intend. Run the health check, verify green status across all providers, then proceed. Next, we get into something that fundamentally changes how you work with AI over time: persistent memory across sessions. Here's the problem that every developer hits after their first week with an AI coding assistant. You close the session, and everything you taught it is gone. The architectural decision you explained, the name convention you established, the reason you chose PostgreSQL over MongoDB for this project, gone. Every new session starts from zero. Claude solves this at the infrastructure level. It's a memory module that integrates directly with Octopus and persists context across completely separate sessions, stored as structured memory objects in a local database, not just raw text. This means Octopus doesn't just remember what you said, it remembers why you made a decision, what alternatives were rejected, and what constraints are in play. Think of it as giving your AI collaborator a permanent notebook that travels with the project. The difference between an AI that asks the same clarifying questions every session and one that already knows your project's context is the difference between a tool and a collaborator. Configuring Claude Mem is a 4-step process, and the configuration lives in your project's Octopus config file, not globally. That's intentional. Memory is project-specific. Step 1. Install the Claude Mem package alongside your Octopus installation. Step 2. Add the memory block to your Octopus config. This specifies the storage path, the memory schema version, and which types of context to persist. Step 3. Define your memory categories. Octopus ships with defaults, architecture decisions, rejected alternatives, active constraints, team conventions, but you can customize these. Run Octopus mainit to create the memory database and import any existing context you want to seed it with. From that point forward, every significant decision Octopus makes, or that you explicitly log, gets written to memory. And here's the part that changes your workflow. You can query memory directly. Ask Octopus, why did we choose this database? And it retrieves the stored rationale from 3 sessions ago. Let's be precise about what Claude Meng actually solves versus what it doesn't. Standard context windows, even large ones like Claude's 200K tokens, are ephemeral. The moment a session ends, that context is gone. And within a session, stuffing a 200K context window with project history is wasteful. Most of it is irrelevant to the current task. Claude Meng operates differently. It stores only the high-value, durable facts about your project and retrieves only what's relevant to the current task. It's not a replacement for context. It's a complement. Think of the context window as working memory and Claude Meng as long-term memory. They serve different functions and work together. The limit of Claude Mem is that it stores what you or Octopus explicitly log. It doesn't magically capture everything. Discipline and logging decisions pay compound interest over weeks of development. In the next chapter, we'll see this memory system in action inside dark factory workflows. Persistent context becomes the difference between a pipeline that knows your project and one that's essentially starting from scratch every run. Here's a question most developers never ask. What if you could hand a specification document system and walk away, and come back to find production-ready, tested software waiting for you? No prompting, no babysitting, no intermediate decisions. That's exactly what the dark factory pipeline in OctoSpark delivers. The name is borrowed from manufacturing. A dark factory is a fully automated plant that runs lights out, zero human workers on the floor. The Octo Factory command applies that same philosophy to software. You feed it a spec, and the orchestration engine takes over every downstream decision: model selection, code generation, test execution, validation, and final packaging. The critical insight here is that this isn't just automation of individual steps. It's the removal of the human from the critical path entirely. And that changes not just speed, but the nature of errors you get. But the question you should be asking right now is, what happens when the pipeline hits something it wasn't designed for? We're going to answer that in detail. Keep watching. Let's trace a real factory run step by step, so you can see exactly where the intelligence lives. Stage 1. Spec parsing. The orchestrator ingests your specification, plain text, markdown, or a structured YAML schema, and extracts intent, constraints, and acceptance criteria. It doesn't just read the spec, it builds an internal dependency graph of every feature and its relationships. Stage 2. Code generation. Multiple AI models are dispatched in parallel, each generating candidate implementations for different modules. This is not one model writing everything, it's a team of specialists working concurrently. Stage 3. Test execution. The generated code is immediately run against a test harness. If the spec included acceptance criteria, those become integration tests automatically. Stage 4. Consensus validation. Outputs from multiple models are cross-checked. If two models produce divergent results for the same module, that conflict is logged and resolved through a tiebreaker model. Stage 5. Final packaging. The validated artifacts are assembled, documented, and delivered to your configured output target: Git branch, an artifact registry, or a local directory. Each stage has a hard timeout. The pipeline never waits indefinitely. And here's where it gets interesting. What happens when a stage fails mid-run? 3 failure modes come up repeatedly in dark factory runs, and developers are often surprised by how they're handled. First, spec ambiguity. If the parser can't resolve intent for a given requirement, it doesn't halt. It generates a clarification request, logs it, and proceeds with the most conservative interpretation. You get a working artifact plus a list of assumptions made. Second, test failure after generation. If code fails its test harness, the pipeline doesn't surface that to you immediately. It retries with a different model, appending the failure context to the new prompt. You only get escalated to if all retry attempts fail. Third, consensus deadlock, when no majority emerges from model outputs. In that case, the pipeline selects the output with the highest internal confidence score and flags the result as needing human review. The pattern is consistent. Try autonomously first, escalate only on total failure. This is what separates a real autonomous pipeline from one that just asks you questions every few minutes. In the next section, we're going to go beyond factory runs and look at the adversarial workflows, and the Octo debate command is something you have not seen in any other AI tool. When every AI model agrees, that's not a sign of quality, it's a warning sign. Models trained on similar data will converge on the same wrong answer with equally high confidence. The Octo debate command was built specifically to break that convergence. Here's how it works. You submit a decision, an architectural choice, an API design, a security policy, and the orchestrator assigns 2 or more models to opposing positions. One model is instructed to argue for the approach. Another is instructed to find every way it could fail. They don't just generate opinions, they respond to each other's arguments in structured rounds. After the debate concludes, a synthesis model reads the full transcript and produces a final recommendation that incorporates the strongest objections as explicit risk disclosures. Think of it as a red team and a blue team running simultaneously, and you get the debrief without sitting in the room. Here's the surprising part. In internal testing, Octo debate surfaces critical edge cases in roughly 6% of architectural decisions that single model review missed entirely. If you're making any non-trivial design decision with a single AI opinion, you are flying blind, and the next scene will show you exactly how the security audit workflow compounds this. Generated code has a specific vulnerability profile that handwritten code doesn't. AI models tend to reproduce common patterns from training data, and some of those patterns carry well-documented security flaws. The Octo security workflow runs an OWASP-aligned vulnerability scan across every artifact the factory produces. It doesn't just grep for known bad strings. It runs a semantic analysis pass that understands context, so it catches a SQL injection risk, even when the injection vector is 3 function calls deep, not on the same line as the query. The checklist it runs covers SQL and NoSQL injection, broken authentication flows, sensitive data exposure in logs or responses, insecure direct object references, and misconfigured security headers. Each finding is reported with a severity rating, the exact code location, and a suggested remediation. Critically, high-severity findings block the pipeline from completing. The artifact does not get delivered until either the vulnerability is in a subsequent generation cycle or a human explicitly overrides the block. This is not a linter. This is a security gate. And the next workflow, TDD, is what ensures the fix doesn't break the behavior that was already validated. Test-driven development is one of those practices everyone agrees with in theory and skips under deadline pressure. The Octo TTD command removes that choice entirely. When invoked, the orchestrator generates failing tests first, before a single line of implementation exists. The tests are derived directly from the spec's acceptance criteria. They are written to fail. Then, and only then, does the implementation generation begin, with the failing test suite as its hard constraint. The model cannot deliver passing output by cheating. It has to satisfy the tests as written. What you're seeing on screen now is a representative example. The test file is generated. It references functions that don't exist yet, and every assertion fails. The implementation model then writes code specifically to make those assertions pass one by one. The red-green refactor cycle is enforced programmatically, not by developer discipline. The result is that every function in your generated codebase has test coverage that was written before the implementation, which is the opposite of the coverage as afterthought pattern that plagues most AI-assisted codebases. In the next section, we step back from code generation and look at how the research workflow gives you the same multi-model rigor for information gathering. When a developer asks a single AI model a technical research question, they're essentially asking one person who read a lot of books. But those books had a cutoff date, and that person has a well-documented habit of making things up when they're not sure. The Octo research command takes a fundamentally different approach. When you submit a research query, the orchestrator fans it out simultaneously to multiple sources. Perplexity for live web-indexed results, OpenRouter for accessing specialized models with domain-specific training, and optionally your internal knowledge base, documentation corpus. Each source returns its findings independently. The orchestrator then runs a synthesis pass, not just summarizing, but actively cross-referencing. If Perplexity says a library's latest version is 3.2 and an OpenRouter model says it's 3.0, that conflict is not averaged away. It's surfaced explicitly with both those citations. The synthesis output includes a confidence rating per claim, and any claim that can't be corroborated by at least 2 sources is marked as unverified. This is not a convenience feature. For technical decisions, especially around security patches, deprecations, or rapidly evolving APIs, single-source AI research is a liability. But you might be wondering, does more sources always mean better answers? The comparison in the next scene will challenge that assumption directly. Let's put single-source and multi-source research side by side, because the difference isn't just about accuracy. It's about the nature of the errors you get. With single-source AI research, errors are silent. The model produces a confident, well-formatted answer with no indication that it's extrapolating, hallucinating, or working from stale data. You can't tell the difference between a fact and a fabrication without independently verifying everything, which defeats the purpose of using AI for research. With multi-source orchestrated research through Octo research, errors become visible. When sources disagree, the conflict appears in the output. When a claim can't be corroborated, it's labeled unverified. When data has a known cutoff, that's stated explicitly. The output is less clean, and that's by design. An uncertain answer that tells you it's uncertain is infinitely more useful than a wrong answer delivered with confidence. There's a practical implication here. Multi-source research takes longer to run, and the output requires more reading. The trade-off is that you can act on the results without a secondary verification pass. As you head into the final chapter, consider this: knowing how these workflows function in isolation is only half the picture. The real question is how you sequence them in a production team without creating new bottlenecks. That's exactly what Chapter 6 will tackle, and the answer will likely change how you structure your entire AI adoption plan. Here is the question every team asks after seeing Octopus in action: do I actually need all of this? The honest answer is, not always. If your task is linear, low risk, and completable in a single context window, a single Claude call is faster, cheaper, and easier to debug. The orchestration overhead only pays off when you cross specific thresholds. When the task requires parallel subtasks, when the cost of a wrong answer is high, or when you need adversarial to catch blind spots. Use this decision table as your filter. Low complexity plus low risk equals single agent. High complexity or high stakes equals bring in the full Octopus stack. The trap most developers fall into is defaulting to orchestration for everything. That is the AI orchestrator trap this entire lecture has been about. Complexity should drive architecture, not the other way around. Now watch what the adoption path actually looks like for a real team. So your team is convinced. Now how do you actually roll this out without breaking production workflows, overwhelming engineers who are new to multi-agent thinking? The answer is a 4-phase incremental rollout. Phase 1. Start Claude only. Get comfortable with prompt equality and context management before adding any orchestration layer. Phase 2. Connect one free provider, Gemini, Flash, or DeepSeek, and run parallel tasks on non-critical work. Feel the cost savings and latency differences. Phase 3. Pilot the Octodebate command on one real decision your team makes weekly. A code review, an architecture choice, a bug triage. Let the debate surface disagreements you would have missed. Phase 4. Once trust is built, unlock dark factory automation for your highest volume, lowest ambiguity workflows. Each phase is a checkpoint. Do not skip phases because a demo looked impressive. Real adoption is measured in weeks, not hours. And the payoff, the key takeaways that tie everything together, are coming right now. Let's crystallize everything. 6 chapters, 1 thesis. Most developers building AI systems right now are flying blind with a single agent and calling it done. Here are the 5 concepts that change that. First, blind spot elimination. No single model sees the full picture, so you must architect for disagreement. Second, consensus gates. Do not let the pipeline advance until independent models agree, because silent hallucinations compound. Third, the 4D methodology. Decompose, delegate, debate, decide. This is the structural backbone, every reliable multi-agent workflow. Fourth, dark factory autonomy. When your pipeline earns trust, you can remove the human from the loop entirely for defined task classes, and that is where the real throughput lives. Fifth, free provider scaling. Gemini, DeepSeek, and Grok are not backup options, they are cost multipliers that make high-volume orchestration economically viable. These 5 ideas together form a complete shift in how you think about AI reliability. And the final step is the one you take right now. Here is your action checklist, not theory, not someday, but today. Step 1. Install the Octopus plugin into your Claude environment right now. The GitHub repository is at github.com/octopus. Everything you need is there, including setup docs and example workflows. Step 2. Run your first Octodebate command on a real problem your team is facing this week. Do not use a toy example. Use a real decision and see what the disagreement surfaces. Step 3. Configure one free provider, Gemini Flash, takes under 10 minutes to wire in, and run a cost comparison against your current Claude-only spend. Step 4. Join the community. Watch the Issues tab, read the work samples others are posting, and contribute your own pilot results. The developers who will build the most reliable AI systems in the next 2 years are the ones who treat orchestration as an engineering discipline, not a prompt engineering shortcut. You now have the framework. The only remaining variable is whether you use it. Go build something that does not fly blind.